Hello, everyone, and welcome to this explainer. I am absolutely thrilled to have you here with us today. Look, if you're an undergraduate engineering student just stepping into the incredibly fascinating world of communications engineering, you are in exactly the right place. Today, we're embarking on a really vibrant, micro-to-macro journey to understand what is literally the lifeblood of the modern digital world. Our explainer today is titled Introduction to Data Communication. We're going to start incredibly small, looking at just a single isolated message. And by the end of our time together, well, we'll have zoomed all the way out to understand the massive, highly complex, interconnected infrastructure of the global internet. It's a lot of ground to cover, but it's going to be a lot of fun. So let's dive right into this, shall we?
Okay, here is our roadmap for today. Number 1, basics of data communication. Number 2, network performance and reliability. 3, physical network topologies. 4, network types and switching. And finally, number 5, global internet infrastructure. Let's get started.
Section 1, Basics of Data Communication.
All right, let's zoom all the way in to the lowest possible level. How does an isolated message successfully get from point A to point B? To make any digital information exchange happen at all, data communication systems absolutely rely on 5 vital components. And this is crucial for you as engineers. If you're missing even one of these, the entire communication breaks down. There's no exception. First up, you need a message. This is the actual information, the data itself. It could be represented as bits, audio, video, text, whatever it is you want to communicate. Second, you have the sender. That's the device generating and actually transmitting that message. Third, the receiver. Naturally, the device on the other end waiting to accept it. Fourth is the transmission medium. This is the physical path carrying the signal. It could be a copper wire, fiber optics, or even the wireless airwaves. And fifth, well, the fifth one is the protocol.
Now, take a look at the way the sender and receiver interact here. That fifth component, the protocol, it's essentially just a set of rules governing the communication. It's the rules of the road, so to speak. You can have a sender, you can have a receiver, and you can even have a totally flawless transmission medium between them. But if they aren't speaking the exact same language or following the exact same rulebook, that message you're sending, it's just meaningless noise to the receiver. They both absolutely must agree on Rule 1, Rule 2, all the way down to Rule N, just for the message traveling across that medium to actually be understood.
So once we have all 5 of our components lined up, we have to make a big engineering decision. How exactly is the data going to flow between them? As communication engineers, you're going to be working with 3 specific directions of data flow. First up is simplex, which is strictly one-way traffic. Second is half-duplex. This is where both devices can transmit, but they have to take turns doing it. And third is full duplex, where both devices can actually transmit simultaneously.
To really lock this in, let's use some everyday analogies. For simplex, think of a mainframe computer sending data to a monitor. The monitor only ever receives data. It's never sending information back to the mainframe. For half-duplex, it's exactly like using a pair of walkie-talkies. You press the button, you say your piece, you say over, and then you wait for a response. The really great thing about this setup from an engineering standpoint is that the full channel capacity is entirely dedicated to whoever happens to be speaking at that exact moment. Finally, full duplex. That's just like a standard telephone call. You can both talk and listen at the exact same time. But keep in mind, that means the channel capacity has to be shared in both directions continuously, which is a key consideration when designing your network.
Section 2, Network Performance and Reliability.
So before we start physically wiring these devices together out there in the real world, we have to ask ourselves a pretty fundamental question. As engineers, how do we actually measure if a network is, good? A true engineering masterpiece isn't just about raw speed. We actually evaluate networks based on 3 core criteria. First is performance. We measure this by transit time, which is how long a message takes to travel, and response time. And this depends heavily on things like user count, the medium you've chosen, and the hardware capabilities. Second is reliability. Now, we measure this not just by how often the network fails, though that's important, but crucially, by how fast it can recover from a link failure. A fast recovery is everything. And third, security. Think about it. A blazing fast, highly reliable network is completely useless if it doesn't protect the data from unauthorized access, damage, or loss.
To hit those 3 criteria, we have to choose our physical connections really carefully. You basically have 2 options. A point-to-point connection is a dedicated exclusive link between exactly 2 devices. The entire capacity of that link is reserved for them alone. Nobody else gets to use it. In contrast, with a multipoint connection, more than 2 devices are sharing a single link. Because it's shared, the network capacity has to be divided up. You can divide it spatially, where devices use fractions of the bandwidth at the same time, or temporally, where they basically take turns using the whole bandwidth.
Section 3. Physical network topologies. Okay, now we're zooming out from just a single link to look at how we physically arrange multiple devices in a room or maybe a whole building. We call these our topologies. We're going to run through a rapid-fire sequence of these, starting right here with the mesh topology. In a fully connected mesh, every single device has a dedicated point-to-point link to every other device on the network. The math here is absolutely vital for you to remember. The number of links required is n times n-1, all divided by 2. So if you have just 5 nodes, plug that in, you need 10 links. This setup provides massive redundancy and ultimate privacy because every single conversation has its own secure, dedicated wire. But as you can probably imagine, the sheer amount of cabling required scales exponentially. It can become a total nightmare to install.
Now contrast that massive cable mess with the star topology. Here, each device still has a dedicated point-to-point link, but only to a central controller, like a hub or a switch. Think of this exactly like your dorm room Wi-Fi router. It is incredibly easy to install and super easy to reconfigure. It's also quite robust for the individual nodes. I mean, if your laptop disconnects, the rest of the room stays online just fine. However, the obvious, glaring engineering flaw here is the total dependency on that single central hub. If that central hub fails, the whole system goes down. No way around it.
Next up is the bus topology, which actually utilizes that multipoint model we discussed just a minute ago. In a bus, a single long cable acts as a backbone that links all the devices together via drop lines and taps. It's incredibly cheap, it's easy to install, and it uses far, far less cabling than a mesh or a star. But there is a massive catch you need to be aware of. If a failure occurs somewhere along that single backbone cable, fault isolation is a complete headache. The entire line might go completely dead, and finding the exact spot where the break happened can be surprisingly difficult. Finally, to finish our topology showcase, we have the ring topology. In this setup, each device has a dedicated connection only to the 2 devices immediately next to it, forming a closed circle. A signal passes sequentially around the ring, typically in just one direction, and it's aided by repeaters at each node to keep the signal strong. Now, fault isolation is actually a bit simpler here compared to a bus network because the device will know pretty much immediately if it stops receiving signals from its immediate neighbor. But beware, a single break anywhere in that ring can completely disable the entire network's ability to circulate data.
Section 4. Network types and switching.
So we know how to connect devices in a room or a building, right? But how do we scale this up? How do we connect entire buildings or cities or even continents? This brings us to the 2 foundational network types you'll encounter everywhere, LANs and WANs. A LAN, or local area network, is usually privately owned. It links devices in a single office, a single building, or maybe a campus. It's heavily restricted in size, usually just a few kilometers max, and historically it offers very high data rates to allow local sharing of hardware and software. On the completely opposite side, a WAN, or a wide area network, provides long-distance transmission over huge geographic areas. We're talking countries, continents, or the entire globe. These WANs can be point-to-point lease lines or incredibly complex switch networks.
Now, the really crucial point to grasp here is that today it is extremely rare to see a LAN or a WAN operating in total isolation. They are almost always physically connected to one another. For example, a LAN on the West Coast and a LAN on the East Coast can be bridged together by routers connected across a massive point-to-point WAN. When 2 or more networks are connected together like this, they create what we call an internetwork, or, more simply, an internet, lowercase I.
But how does the data actually navigate its way through these massive internetworks? An internetwork relies on switches to connect links and forward data from one place to another. And this sets up what I like to call the ultimate engineering showdown. There are 2 primary ways data gets routed through these massive networks: circuit-switched networks versus packet-switched networks.
Let's look at circuit switching first. In a circuit switch network, a totally dedicated connection, either a physical or a logical circuit, is established and remains constantly available between the 2 end systems for the entire duration of the communication. The switch basically just makes that circuit active or inactive. It's very much like an old-school landline telephone call. Once you dial and connect, that pipe is yours exclusively until you physically hang up the phone. This ensures continuous delivery of data without any interruption because the path is reserved just for you. Now contrast this heavily with packet switching, which, by the way, is the absolute foundation of modern computer networks. Here, communication isn't a continuous dedicated stream at all. Instead, the data is chopped up into small independent blocks called packets. Think of it like taking a plastic toy apart, putting every single individual piece into its own separate envelope, and mailing them all independently. Because each packet is an independent entity, switches and routers can function using a method called storing and forwarding. They receive a packet, they store it in a queue for a moment, and then they send it out on the next leg of its journey as soon as the line is clear. This approach allows for incredible flexibility and highly efficient sharing of high-capacity lines among lots of different users.
Section 5. Global Internet Infrastructure. All right, it is time for the ultimate macro zoom out. We're going to look at the largest packet-switched internet network on the planet. And note, we capitalize Internet with a capital I when we are referring to the specific global internet network that connects millions of individual networks worldwide. This global infrastructure is almost unimaginably complex, but it actually operates on a very strict hierarchical structure of Internet Service Providers, or ISPs. At the very top of the food chain, we have Tier 1. These are the massive national and international backbone providers. Just below them is Tier 2, which are the regional providers who pay to connect to Tier 1. And finally, at the bottom, Tier 3. These are the local ISPs that actually provide the connectivity to end users like you and me. Bringing this all together, look at this massive structure. At the very bottom, you have local customer networks. These are the LANs in our homes, our dorms, and our offices, using the very topologies and protocols we just discussed. They connect into the provider networks, which act as those Tier 3 and Tier 2 ISPs. Those, in turn, connect at specific peering points to the massive Tier 1 backbones spanning the globe. It is literally billions of independent devices sending countless packets of data, all finding their way through this staggering hierarchical structure every single second of every day.
Now, keeping this massive machine running requires serious global administration. Organizations like the Internet Society provide the overarching leadership. The Internet Architecture Board defines the technical direction. The IETF handles all the day-to-day operational problems. And the Internet Research Task Force, or IRTF, focuses on long-term protocol research. Which leaves us with a final, pretty provocative thought. We've gone from looking at a simple point-to-point message all the way out to a global, hierarchical internet network. As groups like the IRTF research fundamentally new protocols, how will this global infrastructure need to evolve to handle the sheer volume and complexity of the next generation of data communication? It's a massive puzzle, and it's a question that you, as our future communication engineers, are going to be tasked to answer. Thank you so much for joining me on this explainer. I really hope this foundational overview has sparked your curiosity. Keep learning, keep questioning, and I'll catch you next time.